Alright, scholars, so this is it. The last series of videos. The last time you're going to hear my smooth, soothing, jazzy voice. The last time you're going to sit down to take one of those quizzes that you all love so much. So to end this course, we're going to be discussing yet another form of wave phenomena, light. We're going to discuss how light turns out to exhibit wave-like properties, how we know that, how that affects our everyday lives, and then we're going to analyze how humans have learned to manipulate light, use light to communicate at the speed of light, how to transfer information. And in the past 150, 200 years, this technology has literally changed and revolutionized the world. This technology is why we're able to have this online class, and this technology is why you stare at your magic rectangles, your phones, 24/7. So maybe in some ways this technology has not made the world a better place. I don't know. It's up to you to decide. Let's begin by talking about light. In order to do this, we need to first get a quick review of waves. I know that this is like the third or fourth week that we've gone over waves, but really important that you remember a wave is simply defined as a form of energy passing through a substance, which we call the medium, causing the particles of that medium to oscillate, to vibrate, to move back and forth, right? Well, today we're going to discover that light is actually a special form of wave, which we refer to as an electromagnetic wave, and it actually does not require a medium through which to travel. It does not require matter at all. Light can travel through empty space. We know this because we're receiving the light energy from the sun right now, and guess what? Between us and the sun is nothingness, it's empty space. So light can definitely travel through empty space. It does not need matter to travel through. It does not need a medium, a physical medium. Unlike sound waves, which we analyzed last week, here's an example of a longitudinal sound wave, where every dot here represents a particle of matter, like the particles in the air. It is those particles that oscillate, that carry the wave energy, that transmit the information due to an object vibrating. All waves are like that. They require matter, they require particles to move back and forth, except for light. Light does not. So light is kind of strange, funky, and odd. People have been debating about the nature of light for thousands of years. Our dear friend Isaac Newton, you all remember Isaac Newton, he's the one who discovered the laws of motion. We analyze forces and acceleration and all that stuff. Isaac Newton basically created physics as we know it, and he thought that light was actually composed of little tiny pieces, little tiny particles. He did not think that light should be considered a wave, and we now know that he was wrong. Or was he? We will see. So light is this special form of wave, and it's very, very strange. It does not require matter to travel through like most waves, and people have been debating about what it is for thousands of years. So let me clarify something. When I say that light does not require matter to travel through, it doesn't require particles, it does not cause particles to jostle back and forth like a sound wave does. That's true that light does not require matter to travel through, but it still travels through something. And that something we refer to as the electromagnetic field. Now this is bizarre, strange, crazy, and a little abstract, so you're going to have to use your imagination with me. But the electromagnetic field is this field of potential, the possibility for something interesting to happen, the possibility for electric and magnetic changes to occur. It's a field of potential and possibility that's spread throughout the entire universe, that's spread throughout all of space. That's the electromagnetic field. It turns out that light is a ripple or a wave or an excitation of that field caused by charged particles and magnetic substances. So the idea is that a charged particle is like an electron, right? Remember our charged subatomic particles, electrons, protons? It turns out that charged particles, usually electrons, if they exhibit certain behaviors, if they do specific things, move back and forth, they're capable of exciting this electromagnetic field and causing a wave or a ripple to travel throughout it. This wave can be thought of as a form of pure energy, and this wave is actually light. So let me try to give you an idea of what I'm talking about here. Let's say I have an electron. You can see that we can think about this electron as a little particle with charge that is in some way manipulating this diffuse, spread out field all throughout the space around the electron. So the electron is doing something, it's causing a change in this field. If I were to put a proton, a positively charged particle in, you know that protons are attracted to electrons. Well, this is why. You can see that that the field now is kind of pointing towards, it always has a direction. It's pointing from the proton to the electron, which means that the proton would be capable of moving towards the electron and getting attracted to it. Does that make sense? You guys know that positive and negative particles attract. So that's kind of what the field is. It's this potential for change. Because there is an electron there, there's the potential for interesting things to happen. And it's all due to the electron. If I remove the electron, that potential goes away. If I have an electron, there's this potentiality that has a direction. That's the electromagnetic field. Well, imagine that this electron was moving, that this electron itself was oscillating up and down. Then you can see that the field would constantly be changing up and down. The field itself is oscillating. The field itself is vibrating. The field itself has this constant change. And this, I'm not able to show you this exactly, but that change, that oscillation, that excitation of the field would be rippling away from the electron as a wave. So here's my charged particle. Here's my electron. It's sitting still. But as soon as I cause that electron to do something interesting, like maybe oscillate back and forth, move up and then back down, so I'm wiggling the electron around, that's going to, remember what's surrounding the electron, or what the electron gives rise to, this electromagnetic field, right? So if I wiggle that electron around, that's going to cause the electromagnetic field to shift its direction, to be excited, to gain some energy, basically. And that is going to ripple away from the electron as a wave. And it does get weaker as you go out. But that's what light is. That's what an electromagnetic wave is. It's caused by a charged particle doing something interesting, like wiggling around, exciting the electromagnetic field, causing it to get strong, weak, causing it to change directions. And that propagates out as a wave, as an electromagnetic wave, away from the charged particle. Really crazy, right? The first person to think about electromagnetic fields and things was this dude named Michael Faraday in the 1800s. He did very, very careful experiments with magnets and current-carrying wires. He's the first one to make a true electric motor, to use electricity and magnetism to cause motion, all this stuff. This would be a magnet, and these little black specks are iron filings, little pieces of iron. And he realized that the iron filings always align themselves in this kind of funky arrangement. And this is really actually a visual representation of that electromagnetic field. These are field lines. So magnets have something to do with this field. Electricity has something to do with this field. You guys know that charged particles, electrons. Whenever electrons move, that's electricity. So this has to do with electricity, with magnetism, and what Faraday and then another guy named Maxwell actually ended up realizing is that these fields are not static, but rather they propagate out as a wave that travels very, very fast, and it's a light wave. It is light. So thanks to Faraday, thanks to someone who studied him, James Clerk Maxwell, thanks to these guys, we know that light is the excitation of the electromagnetic field, and it travels out as a wave. So light is a wave. Here's kind of a summary of all that. Light is a wave-like excitation of the electromagnetic field caused by the behaviors of charged particles. Therefore, we refer to light as an electromagnetic wave. This wave has both electrical and magnetic potential components. You don't need to worry about that last part. This little diagram is really confusing, but it's trying to show you that a wave of light has this electrical field dimension, and going perpendicularly to that, so this is like coming out at you and going back into the screen, is a magnetic field component, and the light wave travels like this. It's an electromagnetic wave. It's a wave due to the excitation of the electromagnetic field. It has electrical potential, magnetic potential. The moral of the story is that electricity, magnetism, and light are all kind of unified into a single phenomenon, as strange as that sounds. The most important thing here is that light exhibits wave-like behaviors and properties. So think about all the properties that we've studied of waves. Light has those same properties. Light travels with the speed, just like waves travel with the speed, right? We said that the speed of sound through the air is about 340 meters per second. Check out the speed of light, y'all. 3 times 10 to the 8th meters per second. That's 3,000,000,000,000 meters per second. It's freaking fast, right? And in fact, we now know that this is the universal speed limit. Nothing can go faster than this in the whole universe. Light travels as fast as anything can. And you know that there's an equation that relates the speed of a wave to two other properties of a wave, the wavelength and frequency. The speed of a wave given by v, velocity, is equal to lambda times f, where lambda is wavelength, f is frequency. Remember, wavelength would be measured from peak to peak, the length of one complete wave cycle. Frequency, do you remember what that is? That's the number of wave cycles per second. So if we take this, we can kind of get a special case for light, that the speed of light, which is abbreviated by the letter c, equals the wavelength of light times the frequency of light. Simple enough. So yeah, light has a wavelength that we can measure. It has a frequency that we can measure. It has intensity, which is kind of like light's version of amplitude. Do you remember what amplitude was? Amplitude was the maximum deviation away from the equilibrium position. So this would be the amplitude right here, this distance, how tall is the wave. Light works a little bit different, but its analogy to amplitude is intensity, which you can think of as brightness of light. And just like any other wave, light carries energy. Light is a form of energy, just like waves are a form of energy. It turns out that the energy of light, we're going to talk about this later, is directly proportional to the frequency. Directly proportional to the frequency. So as the frequency goes up, the energy carried by the light goes up. Now that's a little different, right? Do you remember what energy was associated with in our other types of waves? Yeah, it was associated with amplitude. In other waves, like sound or anything else, the amplitude was associated with energy. Not so for light. It's the frequency of the wave associated with energy. If frequency and energy are directly proportional, and frequency and wavelength are inversely proportional, then wavelength and energy are inversely proportional. So the higher the wavelength, that means the lower the frequency and the lower the energy.